So everyone, welcome to the Planetary Sample Science Seminar Series. I'm Quentin, I'm your host. I'm Chip's PhD student here at the University of New Mexico. Today we have Carolyn Crow, who is joining us. She is currently an assistant professor at the University of Colorado Boulder in the Geological Sciences Department. She's interested in geochronology and impacts on the moon and Earth. She recently received an NSF Career Award to expand her research on terrestrial impact craters, and she's received a Planetary Science Enabling Facilities grant to establish a noble gas lab for analyzing planetary samples. And last but not least, she is a part of the Chloe survey team. And with that, Carolyn, go ahead and take us away.
Thanks. Thanks for that great introduction, and thanks for inviting me to give this talk. When I was looking at my slides this morning, I realized I missed one giant big word to put in my title, which was to put dating in front of impacts. So today, basically, I'm going to be talking about a few different kind of large consortium projects that I've been working on that tries to use the vast range of tool sets that we have, both geochemically, geochronologically, and petrologically, to try and date impacts in planetary materials. And as you can see from the bottom, just on this initial slide, this is work not just by me, but by a huge range of collaborators and co-authors, some in the room with you guys in New Mexico. So let me give you a little bit of a motivation for why. Give me just a second. There we go. Why dating impacts, and why do we need these coordinated studies to date impacts? So impacts, right? This is a picture from Gordon Azinski's 2022 paper. Impact craters are complicated. They're complicated geologic settings. They produce a huge range of samples, what we call impactites, that have very different pressure and temperature histories. And these temperature histories are very different than most of the typical geologic settings that we think about in terms of tectonics, erosion, magnetism. They can be very different, right? And they can be complex, and they can exist within these heterogeneities in terms of histories can exist within a hand sample, within an outcrop, and definitely throughout an impact structure. Okay, so they're very complicated. Add on top of that, initial complication in terms of the types of rocks that are being produced. On Earth, we also have all these other processes like tectonics and erosion that start erasing this record of rocks that we have. So most of the impacts on Earth are not like Meteor Crater up at the top. They're not pristine. They don't retain all of the rocks that were formed in the localities in which they were formed. We have things that are like Sudbury, which has been tectonically altered, and we have things that have been eroded, like the Vredefort impact structure in South Africa. Okay, and this says two different things. This kind of subsequent modification can, from a geochronologic perspective, erase signatures that we're looking for, reset systems that we want to use for dating. And it also serves to remove material, right? And so one of the things that's difficult about dating terrestrial impact structures is you kind of get what you get, right? What rocks are still available, and then can we apply the systems that we use to date them? And further complicating, right, the problem is that not all of the rocks that these impacts occur into happen to occur in rocks that we can date easily, right? A large percentage of impact craters are into sedimentary rocks, and we don't have great ways to date them. I have some ideas about that I'd be willing to talk about later. But as a result, like all of these challenges, right, that make dating complicated means that we don't really have a great representation of the ages of impacts. I'm going to see if I can try and mute whoever that is. I cannot mute. We've got some hot mics out there, just so you know. Sorry, there we go. So dating impacts is complicated, but I hope in this talk to convince you can think about this in basically a glass half full or a glass half empty situation. Dating impacts is complicated, especially on Earth. However, we have an ever-growing set of petrologic and geochemical tools that we can use. And if we do these big coordinated studies, we can start chipping away at these problems, okay? Chipping away and trying to find a better way to date impacts, okay? And my motivation so far has been really focused on terrestrial samples. But in this talk, I'm going to actually switch a little bit and kind of pitch that to tackle this problem, we can't just look at samples on Earth. We also have to look at samples from the moon. And the moon, you know, it's basically our witness plate of impact cratering for the last 4.5 or 4.4 billion years, okay? And the surface retains and preserves craters of a whole range of size and complexity. And to really kind of get at this problem, how do you data impact? What are the methods and the tools you can use? We have to use this joint approach of looking at lunar and terrestrial samples. Okay, so that's the motivation for this talk. And basically, I'm going to talk about two different projects, two different kind of case studies of how we are using these tool sets on lunar samples to get at dating impacts. Okay, so let's get to the first study. Okay, and the first study, I'm going to start off with a joke that Chip Shear told me. So this is looking at a lunar meteorite. And Chip came to visit CU a little while ago, and he was sitting in my office, and he said, Carolyn, how many geochronologists does it take to interpret an age? And I said, I don't know, Chip, how many? And he said, none, it takes one petrologist. And I like that joke because it further highlights this importance of you can't just take the age at face value, you have to have context, right? And the context is not just where the sample comes from, but what's the deformation history of the sample, what's the petrologic constraints that you have for understanding the sample. So there we go. So let's talk about this meteorite that I find very fascinating. So this first study, we're looking at NWA 12593. This is a relatively newer lunar meteorite. It is a fragmental lunar breccia. Let me try to move this. There we go. Now I can see my slides. It's a fragmental breccia. You can see it's a breccia. It's got a bunch of clasts in it. It is fused together, has lots of different clasts. Fused together in a fine-grained matrix. We have two slabs of this meteorite. The one that we did the geochronology on is pretty class poor. You'll see pictures of the other one that has more clast within it. This meteorite is moderately to highly shocked. But the reason we're most interested in this meteorite is because it has a ton of accessory phases that we can use for geochronology. It is full of badleite. It is full of zircon. It's got a few zircons, and it is, you know, dozens and dozens of apatites, even in this one little slab. There has been some work done that's been on this meteorite before, looking at chlorine isotopes in the apatite, where they found some really interesting, unique chlorine isotope signatures. That won't be the topic. We won't really discuss that in this talk. But we, as part of our consortium effort, Rita Economist, who's at the University of Hawaii, has been looking at chlorine isotopes and sulfur isotopes as well. Okay, so we have this beautiful meteorite, and I just really want to hammer home like how many accessory phases are in this meteorite, which is great for this study and very impressive. So here's two electron microprobe maps of the sample. And what you can see is every little square here is an accessory phase or a group of accessory phases, either badleites or apatites. And so how many are there? There's a lot. In this one, 3.5 centimeter slab, we have 66 apatites, 105 marilites, 21 badleites, and 2 zircons, which is very accessory phase rich for lunar samples. Okay, so we're going to talk about geochronology of two sets of the accessory phases. We're first going to talk about the badleites. and some of the petrologic and microstructural work we've been doing to understand the ages of the badleites. And I will also then loop in those apatite and marylite samples as well, okay? Okay, so why are we interested in looking at the badleite? Well, there's been a lot of talk about cubic phase heritage in zirconia on the moon and also in terrestrial impact structures. So what is cubic zirconia and why are we interested in it? Well, depending on the crystallization temperature of zirconia, it will have either an initial cubic structure if it's crystallizing at really high temperatures above 2370 degrees C. If it's crystallizing above 1170 degrees C, but below that cubic structure, we will have tetragonal. And then if it's crystallizing at normal magmatic temperatures, less than 1170, we will have a monoclinic structure. So understanding the structure of badleite when it forms can give you some indication of the crystallization temperature. The cubic structure of badleite is not stable at room temperature. So even if it crystallizes in cubic structure on the left, as it cools, it will shift into tetragonal structure by elongating along one of the axes, and then it will shift to monoclinic, okay? And during all of these shifts, right, there's multiple ways. You can stretch when you're switching to tetragonal, you can switch along various axes. When you're switching to monoclinic, you can shift in multiple directions. And what that means is when we look at EBSD data, right, which is basically looking at a projection of like where is the C-axis. If the C-axis was a flashlight, where would it be flashing on this circle on the left? Because we have those different shifts and you can have shifts in multiple directions, instead of a normal pole projection plot where you have one really nice one nice location for where your axis will be, you end up with basically a cloverleaf pattern, which is a relic of basically these shifts in terms of the structure. Okay. So where do we find cubic zirconia? Okay, we find it in terrestrial impact structures. So here is example over on the right of basically a zircon in the center that has been kind of dissociated into badleite, and you can, if you do that kind of pole projection reconstruction, we can actually see these individual groupings of domains that were basically reconstructed, that these domains had original cubic structure and shifted into the more stable badleite structure, okay? And these samples are actually found in superheated impact melts. And one of the constraints on the superheated is the fact that this is basically recording temperatures above 2370 degrees C. So we're pretty confident, at least on Earth, that if you're seeing this cubic zirconia structure in samples, that it is forming potentially at a superheated impact melt sheet. And one thing I didn't mention before in the previous slide is we understand these transitions relatively well. We understand cubic zirconia relatively well because it is a material that is made industrially for a various range of purposes. So from a material science perspective, we do understand this relatively well. Okay, so, this is just showing also that there's, it's not just Mestassen Lake, but there are other impact structures where we see this on Earth. Okay, so what about our sample for NWA 12593? Well, we also see when we look at, these are these pole projection plots for these cubic badleite, or for these zirconia. You can see that we have, hopefully you can see my mouse, you can see that we have these really beautiful cloverleaf patterns instead of a really nicely coalesced point in these pole projection plots, okay? And in order to have cubic structure, right, to confirm cubic structure, you would like to have this cloverleaf pattern for all the possible options. And we have pretty darn close to all of them. So we are very confident that these grains, these cubic zirconia grains within this NWA 12593 meteorite do have that cubic phase heritage, suggesting that they crystallized at temperatures above 2370 degrees C. Okay. I can't see my presenter mode over here, so I'm going to have to flip forward and back sometimes. Okay, so we see these, and that's really cool. And so we are interpreting that these grains are crystallizing potentially in a superheated impact melt sheet and likely are crystallizing in an impact environment. So the next step that we want to do is we want to take these grains and then we want to date them to figure out when was potentially the age of this impact. Okay, and the method that we used was lead or lead isochron dating. And I want to introduce lead isochron dating to those who are not experienced with it and those who maybe have not thought about lunar lead, which is slightly more complicated than terrestrial lead. Okay, so in lunar lead isochron dating, we basically have our three isotopes of lead. We have 207 and 206, which are the decay products of 235 and 238 uranium. We also have 204 lead, which is not produced by radioactive decay. And this 204 is going to be our tracer for non-radiogenic sources, either terrestrial contamination or lead that was initially in the magma from which these samples are forming, okay? And so in lead isotope space, you basically, for the moon, you have three end members that could be contributing to what you're measuring in your SIMS analysis spot, right? Or TIMS, depending on what kind of method you're using. And basically what you have is you have this mixing triangle where the point down here on the left on the y-axis, that is your age, that is that intercept value of the 207, 206 ratio that's telling you what the radiogenic composition is, what is that lead isotopes being produced by radioactive decay, and you can take that and you can turn it into an age. You also have mixing. If you're thinking about looking at multiple phases, you can have mixing with the initial lead. So this is the lead that's in the magma at the time that it grows. And then you can also have terrestrial lead contamination on the surface, or if you're looking at meteorite samples like this one, there's fractures, there's cracks, this has been sitting on the surface for a while. You can get terrestrial lead that mixes in with your analysis. And so in an ideal world, right, we use zircons, right, and zircons don't take any initial lead in, and then if we can clean them very well, then we don't really have to worry about this with lunar zircons. And that's why I've done a lot of lunar zircon work and others have as well. It's not as big of a problem. But once you get to meteorite samples or you start looking at other phases like phosphates can incorporate some initial lead. If you flip back and look at the scale bar for these different badleite samples, here's the scale bar of 5 microns. If we're running with a 5 micron spot, we might be okay and might be able to avoid any fractures, but you can see that there's a lot of fractures here. And so we're going to potentially start getting some of that terrestrial contamination that's in these fractures. So even though we're measuring badleites in this little portion, we are mainly going to use lead isochrons just because of the challenges with how small the spot sizes are. Okay, but that being said, we actually did relatively well. So here's the lead isotopes for the cubic zirconia in this lunar meteorite. And we have the same axes as before, right? Here's your 204. This is where terrestrial lead is. I've put that on there so you can see it. And we actually have most of our samples are actually pretty good. Most of our samples, this is a zoom in over here. Most of our samples do not, we have some really good data points that are really nicely anchoring our isochron down here. They give us really good ages. We don't have to do a huge lead correction. But as you can see, some of the analyses, yeah, we are hitting cracks. We have some terrestrial lead contamination. And there's different ways that you can calculate the age from this. This is one of the ways, and our preferred way, which is we know this sample has terrestrial lead contamination. So we did a projection through terrestrial lead, and we get this really nice age of 3.48 billion years old. Okay, so recap, these are cubic zirconia. That means that they're crystallizing at relatively high temperature. We are interpreting them to have crystallized in a superheated melt, most likely the result of an impact, and they're giving an age of 3.48 billion years. Okay, so that's really a nice, like, solid, cohesive story, but we're not completely satisfied with just that because as one of the points of my talk is the more data, the better. You want to have coordinated analyses. You really want to put as much data into this to understanding the story. Okay, so what about the other phases? Okay, so here you can start seeing why things get complicated when you expand. So this is kind of the same plot. I'll flip back for a second. Okay, so we have this cubic zirconia data, and I've added on to this our phosphates and our zirconium or zircons. We've had 2 zircons in here. And I've also added on glass and feldspar analyses. And those we really use, we try to use in lead isochron dating to really start trying to get at what is this lunar end member, right? The glass, the mesostasis glass will record some amount of will hopefully record basically the lead isotope composition of the magma. But what you can see is as we start moving away from the more ideal phases, we start moving away from the badly, there's zirconium-bearing phases, we start getting a lot more mixing, right? And you can see that there's mixing with some lunar initial lead compositions, and then we get stuff that's falling in this mixing area where we have terrestrial lead, and we have lunar lead, and we have radiogenic. And a lot of these are basically, it's not necessarily, there's not an issue with the analyses. It's just that for some of these phases, like the phosphates, the uranium concentration is so low. So you're really, this signature, this end member mixing is really hard to differentiate. But even though it's messy, we can still get some really interesting information from this, okay? So even though it's messy, this projection, right, if we use this projection from terrestrial along like the bottommost data here, that will give us basically an estimate of what the upper limit of that age is, right? What is this intersection here? Okay, so if I clean this up a little bit, right, and do basically the equivalent of what I was doing with the cubic zirconium before, and do a projection, but now including more data, including some of the phosphate data, we still get a really consistent age, right? I mean, it's slightly younger, but it's got bigger error bars. And so basically what this is saying is that the other phases, the apatites, the marilites, they also agree that there is a 3.48-ish billion-year-old age for this sample, okay? It's not giving us a younger age. And the importance of that is that phosphates are much easier to reset their geochronology than the zirconium-bearing phases. And so a lot of times in lunar samples, what we see is we can see zircons, they're inherited, they're older. Take, for example, like 14311, which is an impact melt breccia. You have zircons from 3.9 to 4.3 billion years old, but all the phosphates are 3.9 billion years old. And so this is really interesting that basically all the phases are consistent with a 3.4548 billion year old age. Okay, so This age of 3.48, I'm just going to list out again as a recap why we think this is an impact age. Okay, so all the badleite has this high temperature phase heritage, suggesting that it all formed at cubic structure, meaning that they all crystallized above 2370 degrees C. The age of all the badleites in here is 3.48. It gives a really good, solid, well-constrained age. And the phosphates in this sample are also consistent with this age. So we are basically using this and say, okay, this is an impact age that is recorded in the sample, pairing together the microstructures and the geochronology. Okay, so so we have this age, but this age is also very important. Like this 3.48 billion year old age is not an age that's isolated to the moon, which is one of the most exciting things. This 3.48, like 3.5 billion year old age also is seen in the terrestrial impact record, and it's also seen in the record of impacts on Vesta. So for example, the oldest spheral beds on Earth, so this is kind of like the oldest material from an impact on Earth that we can constrain the age of, is 3.48 billion years old. And we see this in two places, in the Pilbara and the Capville Craton on Earth, okay? But there's even more. And so here's a big complicated summary figure. But I'm hoping this will highlight why we're so excited about this 3.58 billion year old age. So here we've got age in millions of years. Here's a probability density. All of these red spikes here, those are basically the oldest spheral beds. There's multiple spheral beds on Earth that are older than 3 billion years old. They kind of cluster in these two different clusters, but this older one overlaps with basically this Dresser formation overlaps with our meteorite age. Here's our meteorite age, the NWA 12593, overlaps with it. This bump down here is the oldest, or is an impact age on Vesta. And you can see that in this zoom in up here, where we have basically NWAs, our meteorite age, we have perfectly overlaps with the spheral bed age. It's consistent with an asteroid 4 Vesta impact age. And interestingly, this green line here is basically the age of the oldest fossils that we have in the rock record on Earth. So there's a lot of stuff going on at this time, which is very interesting. It's also important age because this is kind of the time period where the lunar and the terrestrial impact record kind of diverge. There's a gap, right? In the back here is this blue line. These are crater counting ages for large craters. You can kind of see, that they taper off as we're getting closer to 3.5. And this is the oldest thing. So these craters are some of the younger things that we have constraints for in terms of big craters on the moon. And then we have basically the terrestrial record coming in from the left. And so this is really interesting that they are overlapping with each other. And if we could figure out where NWA 12593 is coming from on the lunar surface and what impact crater it is tied to, we can actually potentially tie together these kind of two disparate histories of the Earth and the moon, those two impact records. So I'm going to take like a brief tangent for a second to talk about where we might think that this meteorite is coming from, which will tie in some of the stuff from Chip's joke about petrology, using the petrology to understand where is the sample coming from. So where is this 3.48 billion year old impact, right? We think potentially, right, there's lots of accessory phases. Your first assumption would be, well, there's a lot of accessory phases. Maybe it has creep, maybe it's coming from the near side. But there are some other regions that it could be coming from as well. So just saying, oh, it might be creepy because there's lots of zirconium bearing phases isn't good enough for us. And we're going to dive a little bit deeper into that. Okay. So one of the ways to do this is to look at the clasts within the samples. I'm just highlighting here some interesting clasts that are within this meteorite sample. Here's this accessory phase rich class that has some kind of symplectite-like texture. There's plans to do follow-up studies on this class, but you can see basically there's multiple badleites in this class, which is the yellow. There's apatites in red. There's marilites in that kind of pinky color. There's lots of accessory phases in here. And this is not necessarily the only interesting class. There's another interesting class in the second slab that we bought. Here's a picture of the second slab of the meteorite that we bought. You can see there's some really beautiful big clasts. But we took this sample and we did micro XRF mapping. So you can see that there's a various range of compositions of clasts within this sample. But there's one of particular interest, which is right down here, that it doesn't necessarily stick out in this elemental map, but when you look at zirconium, this is the zirconium map of this sample. You can already see just looking at the zirconium map that this is a very zirconium-rich sample. And this class is basically, it's 0.2 weight percent zirconium, which got us really excited because we were like, hey, if it is 0.2 weight percent zirconium, there must be a ton of zircons and badleites in there to date. Unfortunately, we were disappointed that there isn't really anything to date in this sample. So here's a zoom in of close up. Here's on the left, here's the SEM BSE image. Sorry, it's not labeled. And over here on the right is a zoom in. This is a zoom in zirconium map. And what you're maybe starting to see is that there's zirconium everywhere in the sample, but there is nothing bright sticking out associated with that in the BSE image. So we saw this, we started to get a little disappointed, and we said, okay, we're going to do some even more in-depth mapping. And so here we zoomed in even further to figure out where is the zirconium. On the left is an electron microprobe zoom in map. And you can see there are little zirconium blebs here in yellow, but they're not really associated, with anything. It's basically housed somewhere in the mesostasis. So it was somewhat disappointing from a dating perspective, but interesting from a petrology perspective. So we tried to figure out, okay, what is this really interesting, weird class? And so we looked at the bulk mineralogy or the major element mineralogy, and actually this class both texturally, so here's our class up on the left, and here's a high aluminum basalt class from 14321 on the bottom here. And this is just a comparison. Sorry, I made this plot literally this morning, so I don't have a key on it, but the gray shaded area in here is basically the range of compositions for high aluminum basalts from Dickinson et al. 1985. And right here is in the green and the black is our class, the bulk micro XRF composition of our class. And it pretty nicely matches to high aluminum basalt. Although ours is even more enriched in aluminum than has previously been seen. So this is interesting. So we have lots of zirconium. We have some interesting symplectite class that have a bunch of accessory phases. We have this high aluminum basalt class. how are we going to use this to then like try and figure out and narrow down where is the source region for this meteorite? One of the ways that we could do that is we could look at, well, where are the candidate regions for high aluminum basalts on the moon? So this is a recent paper from Ma et al. 2024 showing basically the spectroscopically identified regions that could source high aluminum basalts. You can see them all outlined here. Most of them are on the near side, associated with various mare regions. There are some regions on the far side. We have taken the first pass at trying to find craters that are big enough to have basically exposed melt, like an exposed melt sheet, or have potentially a Christian, you've got a hot mic. Thanks. A superheated melt sheet that could produce these badleites that are potentially close to these high aluminum basalt areas, and then have an added criteria of having a young crater identified by like high albedo or high rock abundance that could potentially source the meteorite to Earth. And we have two best candidates at the moment, although this is a little hand wavy at the moment, but I think it's interesting to kind of go down this thought process. And our best two candidates are Humboldt crater, which is located here, relatively close to one of these high aluminum basalt regions, as well as La Perouse crater up here. So it's a little more hand wavy, but this is one of the directions that I hope that we can start going with, combining multiple different data sets from the petrologic perspective, the microstructural perspective, and the geochronology perspective, and pairing that with remote sensing data to try and really understand the ages of craters and constrain the ages of craters, which can be hard to do with meteorite samples. The other thing that I will just make a note before we start talking about the second project is that these two craters have crater counting ages that are similar to the NWA 12593 meteorite. So they have crater counting ages of about 3.5 billion, although those have relatively large error bars of plus or minus 100 million years. Okay, so what are our takeaways from the study number one? Well, we have this really interesting meteorite. We are pretty confident in this impact age, but we needed the petrology, the microstructures, and the geochronology to get there. One of these data sets alone would not get us to this understanding, and we probably need to do more petrology to basically make this next jump that we want to, which is figure out where is the sample actually coming from on the surface, so we can really tie that crater counting and the rock record together. So again, this meteorite has a 3.48 billion year old age in the cubic zirconia. It's contemporaneous with impacts on Earth and Vesta. And if we can do this next step of tying this sample to an impact crater on the lunar surface, this is a really interesting sample because it might be able to be a golden spike between the lunar and the terrestrial impact records, which are right now disparate and doesn't have that tie line to go together. Okay. So I'm going to shift directions and just briefly talk about one more study before taking questions. The second study I want to start talk about, I'm going to prompt it with not a joke from Lars Bohr, but I'm going to paraphrase Lars for my motivation, which is I've often had conversations with Lars Bohr where he says, I don't believe in age unless multiple geochronometers agree with each other. And even then, I'm not 100% sure. And if we think back to the motivation slides where we have really complicated rocks that are being produced by impact structures, very heterogeneous pressure temperature conditions, in an impact setting, you are often not going to have multiple geochronometers that agree, but that's not always a bad thing, okay? And My pitch for this study is that you can use these coordinated approaches even when geochronometers are getting disturbed to figure out the history of samples. Okay. All right, so for the second study, this was part of the ANCSA-1 program, which Chip helped lead. So this was looking at these stenocrater basalts. I'll talk about what stenocrater is in a minute. So these are high titanium basalts. They were all chipped off of this boulder on the surface. You can see an astronaut for scale. It's not a very big boulder. They're all chipped off from the top. These 4 samples that I've circled here, we have all 4 of these samples. One of them, this 17036, was frozen upon return. And so this is part of a larger consortium effort to look at many different things about these samples to try and understand, the volatile history of these samples. Can we understand chemical degassing signatures? And my role was basically doing the geochronology as the underpinning for comparison for the volatile studies. But the geochronology ended up being interesting in and of itself, as it always is. So what is stenocrater? Let's get a little bit of context. So here's the Apollo 17 landing site. Here's where they landed, we're at LM. The first EVA went to Station 1, which was right next to Steno Apollo crater. This is a relatively small crater. It's about 0.5 kilometer in size. You can see how rocky and boulder, like the rocky boulders and ejecta, so it's relatively young. And then the samples were basically chipped off of one of these boulders that is ejecta from this small crater. So our goal was to figure out from this basalt, even though it's a boulder on the surface, do all of these samples, are they coming from the one magmatic event, or is it multiple magmatic events? Because oftentimes you can have lots of breccias on the surface. So we did this big coordinated effort where we looked at the microstructures, we did argon-argon geochronology, and we looked at lead isotopes. So for the EBSD characterization, looking at the microstructures, we see a range of various things like badlite, apatites, tranquillityite. Unlike the first study, right, everyone's been talking about cubic phase heritage, everything's cubic phase heritage. Well, these are pretty normal badleites. They don't have any phase heritage. This suggests that this is just a plain old basalt, crystallized at normal basaltic temperatures of less than 1170 degrees C, which is an important context to have, right? This is just the basalt. Let me see if I think my slides are stuck. There we go. Okay, so we use the microstructural characterization, just a regular basalt. Now we went in and dated the zirconium-bearing phases. So we went after these badleites and some tranquillityites. And here on the left, I'm showing you basically the same lead isotope diagram that we did before. Remember, this is actually the axis is here at 0. This intercept, this 207, 206 value is giving us the age. We have some samples that have terrestrial contamination, but not that bad. We actually get a relatively good age of about 3.774 billion years old. If we put all 4 of the samples together, so that was just for one sample, all 4 of the samples, all that were chipped off of the block, of the boulder, they all give consistent lead-lead isochron ages. They all give the same magmatic age, basically confirming, okay, yes, something that we assumed was true, that this is one boulder of one magmatic event. Okay, the interesting part comes in when we start looking at the argon. So we want to compare, right? Lead is a high temperature system. Argon's a lower temperature system. It's going to get reset during impact processes easier. And the thing that surprised us about the argon are 2 things. This is a small crater, right? It's half the size of a meteor crater. It's still relatively large, but half the size of the meteor crater. And we saw a huge range in argon loss behavior. Okay, so if you're not used to looking at argon-argon age spectrum, just look at the one on the left to start with, okay? How we measure this in the lab is we heat it up, incrementally reheat it up. to release the argon gas that's coming off. So as you go from left to right on this isochron diagram, you're going from low temperature to high temperature. In an ideal world, you would have everything, right? Like closed system behavior, no argon loss, everything falls on a straight line in a beautiful plateau, okay? We don't have that in any of our samples, but this is the closest that we have on the left, okay? So I put on here that we have our lead isochron age dashed along there. And you can see, at least for this one basalt, the 71037, we get a really like pretty close to the lead isochron age, especially in these higher temperature, more retentive domains, with a tiny bit of lead loss. But then we look at a rock sample, right? This is the frozen sample that's literally from like right next to it on the same boulder. And we have huge amounts of argon loss, giant amounts of argon loss. I mean, this is, I can't remember off the top of my head, but I want to say it's like 15-20% argon loss. But interestingly, even this one, which has the most amount of argon loss, we are kind of converging towards the lead isochron age in those most retentive steps. Okay. We also did exposure age dating. So as a result, I'll flip back for a second. So as a byproduct of doing the argon-argon geochronology, you also get an argon exposure age. And the exposure age basically tells you how long has the sample been exposed to cosmic rays. So cosmic rays come in, they hit the sample, they interact with the potassium, the calcium, the iron in the sample, and they produce 38 argon. So we can produce basically a similar age spectrum, but it's an exposure age spectrum for these samples, and we get pretty consistent exposure ages of about 56 million years. Okay, what does that mean? That's how long that boulder has been sitting on the surface. It's a little younger than previous krypton exposure age dating, but it's not unusual to have variation in these exposure ages. Okay, I've just threw a bunch of geochronology at you, but let's put it together into a bigger story. Okay, so let's put the microstructures together with the chronology into a story. So here's our Taurus Littoral Valley, where Apollo 17 is. We take that lead age, and basically which is supported by the high temperature argon. So we have mare magmatism in the Taurus Littoral Valley about 3750 sorry, that should be a million years ago. This is also consistent. Here's our study here. Josh Snape, 2019 paper, looked at a bunch of other Apollo 17 basalts, and they all have the same age, right? So the fact that you have multiple samples, consistent ages, suggests that you have this big magmatic event at this time. Then what happens? Well, between 50 and 110 million years ago, depending on what exposure age you believe, we have the Steno impact crater. It excavates boulders from this magma, throws a boulder up on the surface, doesn't really significantly disturb the lead isotopes, but it causes variable amounts of argon loss, okay, surprisingly. But even like this is a very simple history. Magma comes in, sits on the surface for a long time. You have one impact that picks it up and puts a boulder on the surface, and you chip it off. Okay, that's probably the simplest. Even thinking about terrestrial impact craters, this is like the simplest scenario you're going to have for dating. And we can already see that you still need multiple systems, and you still need coordinated approaches to understand even the simplest impact scenario. Okay, so what are the takeaways from this study? Impact heating and age resetting can be heterogeneous from the hand sample to boulder size scale. This is something that terrestrial impact crater experts have known for a while, but we're also, it's nice to see that is also true on the moon. So what is the implication for that? Well, if we're thinking about sample collection strategies, both on the Earth and the moon, we need to sample multiple samples right, from an individual location with enough mass to duplicate analyses. Because we saw, even in the study, you chip off the same area of the boulder, and then I didn't really show, but then you take that little fraction and you divide it into smaller fractions, and we still see variability. So it is extremely heterogeneous on the small scale, which means we need to be able to do lots of analyses. Impacts as small as 0.5 kilometer, which is not very large, especially when you're thinking about the moon, and even on Earth, they can cause significant argon loss, which was unexpected. However, glass half full, if you start pairing all these systems together, argon, lead, exposure rate staining, petrology, microstructures, you can actually put together a magmatic and an impact history for these samples. I'll put the caveat, at least for basalts with simple shock histories like this Apollo 17. And kind of connecting back to the first study, which was looking at breccias, right? Breccias are going to be more complicated, and I really think there should be more consortium efforts to kind of tackle breccias, both in terms of Apollo samples, but terrestrially, because they are going to be, for a lot of terrestrial impact structures, what we have are breccias. We don't have samples of impact melt sheets. And so these, if we can really figure out these complex samples, this is where we're going to make like the most strides forward for dating impact craters. Okay, I think I've got like a few more slides. Just to start wrapping it up, I want to put this motivation slide back up to remind you, like, what was my motivation? What am I trying to convince you of? I hope that through these two examples, I've kind of convinced you that even though dating impacts on Earth and the moon are challenging, that hopefully it's a glass half full situation, that we have tons of petrologic and geochemical and geochronologic tools to help tackle this problem. And we're trying to increase that set even further. And I'm going to do a selfish plug for our facility here at CU. So we just got, but we have recently got funding from the NASA Planetary Science Enabling Facilities grant program to establish a noble gas lab for analyzing terrestrial, extraterrestrial samples and planetary samples here on Earth, where we're hoping to basically expand that toolkit and accessibility to the toolkits to tackle these problems. Our install literally happens tomorrow starting at 9 a.m. So it's kind of poor timing for me to schedule a talk right now. But here's a picture of the mass spec in the room. My students joke and say, this is my second baby in the background. And here's our gas processing line as of yesterday, sitting and baking and waiting for the install tomorrow. We hope to be up and running as soon as possible, but we will basically be a noble gas facility devoted to planetary materials, and we really look forward to training students and postdocs and the next generation of scientists. We have Noble S 5 Faraday 5 multiplier mass spectrometer. We have multiple ways to introduce the sample gases, extract them from samples. We have a CO2 laser for heating samples directly. We have a diode laser for doing some amount of diffusion experiments. We have a laser ablation system. We have cryogenic capabilities to separate gases. We currently have helium, neon, argon, xenon standards and are looking for a krypton standard if anybody has any leads. And for the next couple of years, based on our PSEF, we will be dedicating 50% of our time to planetary science community projects. So we look forward to collaborating with you on these projects in the future. And with that, hopefully I've left enough time for any questions.
Thank you so much, Carolyn. What we'll go ahead and do is open the floor up to questions. So for those of you online, you can raise your hand or put something in the chat. And then for those in person, if you want to throw something at me, you can do that, or raise your hand or whatnot. So
I'm going to stop sharing so I can see people too. I can always put my slides back up, but I can't see anyone.
Oh, go ahead, Carl.
Hi, Carl Agee here. That was really a great talk. I really enjoyed it, and gosh, that lab looks awesome. So, yeah. let us know when it's working.
I will send lots of emails when we
Yeah, so
find
that,
our first data set.
class with the high zirconia.
Yeah.
Isn't that an impact melt class? I mean, it looks like a bunch of quench crystals. So, you know, you showed it to be, I guess, what was it, a high aluminum basalt, but, how much zirconium should be in there? I mean, what's normal and what is considered to be high? Because it seemed like high, but,
Yeah, that's
trying
like,
to understand what
yeah.
that, why is there a lot of zirconium in there? Or is that normal?
That's a great question. It is, and again, I'm not the petrologist in the in the consortium, but it is on the high side, and the sample as a whole is on the high side. I mean, having that many, even just thinking outside of the class, right? Like the class, the breccia and the matrix of the breccia is going to be sourced from the material that the clasts are made out of, and there's tons, right? Like there's tons of badleites. A lot of the badleites are in class themselves. There's a symplectite class. It is higher. You know, there's always we haven't done a deep dive into the high zirconium basaltic class, whether or not it's impact melt versus basalt, and there's going to be, you know, crystal size distribution constraints and stuff on that. But, you know, our first hunch is that the material, there's multiple clasts within the sample that have this high zirconium component. So wherever the material is coming from, wherever that impact is probably going to have more material. I mean, our first guess was that it's coming from a more crepey region. But yeah, so there's definitely more work to be done on that class. I'm sorry if that doesn't fully answer your question, Carl.
Thank you, Carl. Do we have any other questions? Go ahead, Chip.
Yeah. Hi, Carolyn. Thank you again so much for giving talk at the seminar. This has been great. And I particularly liked your first part of your talk since I saw it on a poster that you gave maybe a year ago. But I think it has far-reaching implications for the impact history of the inner solar system. The question I had, though, was tied to your second part of your talk. And, you know, clearly during ANCSA, the team that you were associated with were kind of looking and comparing cold samples that were stored at, you know, minus 25 degrees C for 50 years from those that weren't. In terms of lessons learned, were there any differences between the cold stored samples and the samples that weren't?
Not from a geochronology perspective. And we didn't expect from a geochronology perspective that there would be a difference. And you can see that too, like our sample that has the most argon loss is the one that's frozen, as opposed to the other ones that don't quite have as much. The volatile measurements from that consortium are still in process ongoing, so I haven't fully seen those results, so I can't comment on the volatile perspective at the moment. But yeah, I mean, we didn't necessarily expect to see it in the chronology, and we kind of confirmed that.
Thanks.
Thank you, Chip. Karen, did you have a question?
Yes, and hi, this is Karen.
Hi, Karen.
Hi, question purely out of curiosity. Like when you talked about the transformation from cubic zirconia to prismatic monoclinic, you related that only to temperature. Is there any pressure effect?
Timmons is on the line. He can do that. He could comment on that, but I believe it's more of a temperature than.
I think it's because we didn't mention pressure, but yeah.
Yeah, it's more of a temperature, and we have the temperature constraint better from like industrial material science applications as well. So Mainly, mainly temperature. There will be some pressure constraint. Oh, there we go. Timmons commented. Thanks, Timmons. Where did he say?
Yeah, Timmons says there's a pressure effect, but at 20 gigapascals, you would still need temps greater than 1200 degrees centigrade.
Oh, okay.
Mhm.
Thanks.
All right, thank you, Karen. And then with that, we are out of time. So thank you guys, everyone. Once again, Carolyn, thank you.
Thank you.
And then before we go, we just want to make one more announcement for next week that there is the final seminar of the semester. It is Ananya Malik from University of Arizona. So please join us this time next week, and everyone else have a wonderful rest of your day. Thank you.